Hi everyone. I hope that I will record a pretty short pre-lecture here. What I want to do is just make sure we're all okay at balancing equations by inspection. We'll then talk about what the coefficients in a balanced equation mean, and then how that is going to relate to stoichiometry. So I want to introduce stoichiometry, not going to do much with it, but get you thinking about it as well. So let's just start out by practicing balancing an equation. So let's take this molecule, C8H18. This is octane. Okay. And let's look at the combustion reaction of octane. That means it's going to be reacting with oxygen gas. If it's in just a normal environment, oxygen gas from the air. And we'll talk a little bit about this as we go along. You'll see some combustion reactions as we go through this course. And if we take a compound that's only composed of carbon, hydrogen, and or oxygen. Now this one doesn't have oxygen in it. Your two products of complete combustion are carbon dioxide, and that would be a gas. We could put our phases in here. Octane is a liquid, so we use an L. Oxygen is a gas. We produce carbon dioxide gas, and initially the water would be produced as water vapor. As it comes in contact with air, it would condense to a liquid. So we could write it either as a gas or a liquid, depending on where in the reaction we're thinking about. Okay, so that's the combustion of octane. Let's balance this. Now, for reactions that have hydrogen and oxygen, I would recommend balancing everything other than hydrogen and oxygen first. That means we're going to start with carbon. So on the left, I have a subscript of 8. I have 8 carbons. So we balance with coefficients. Those are the numbers in front. Don't change your subscripts. These subscripts are fixed. If I change the subscript of carbon in CO2, it's no longer carbon dioxide. So we balance by adding coefficients. Let me just choose a different color here. Let's balance with green. So 8 for CO2. That gives us 8 carbons. All right. Now, once you're done with everything besides hydrogen and oxygen, now go to hydrogen. Okay? And we see we have 18 hydrogens. So we're going to need a 9, coefficient of 9. 9 times 2 is going to give us 18 hydrogens. Now let's add up our oxygens. We have 8 times 2, so it's coefficient times subscript. So we have 16 oxygen atoms. And over here we have 9 times 1. So we have 9 more oxygen atoms. Total of 25 oxygen atoms. Okay? So we need then 25 on the left as well. All right? And the reason why we balance in a chemical reaction, and I'll show you the statement here in just a minute, it comes from Dalton's atomic theory. In a chemical reaction, atoms are neither created nor destroyed. Okay? Nuclear reaction is different, but we're going to pretty much spend this entire year on chemical reactions. So the elements we have on the left, or let's say the atoms we have on the left, carbon, hydrogen, and oxygen, we're going to have the same number and types of atoms on the right, because atoms are neither created or destroyed. And the number is going to be the same because of conservation of mass. That also holds true for a chemical reaction. So, 25 oxygens. We need 25. Now you'll notice we have a subscript of 2. It's going to create some problems because you're going to see already, wow, we're going to have a fractional coefficient. So whether you write it as 12.5 times 2 is going to be 25. Or we could write it as 25 halves. 25 halves times 2 is going to give us a total of 25 oxygen, which is going to balance the other side. Is that okay? Can I use a fractional coefficient? Yeah, I mean, at this point we can, because that equation is balanced. If you count, we have 8 carbons on each side, we have 18 hydrogens on each side, and we have 25 oxygens on each side. That is a balanced equation. Now, typically we balance equations with what? Whole numbers. And so I think you can see that we need to multiply by a simple factor to get to whole numbers. And that factor would be a factor of 2. All right. So we're going to multiply all the coefficients by 2. And when we do that, 2 times 1 for octane, 2 times 25 halves for O2 is going to give us 25 O2. I apologize that that's so close to that. Yielding 2 times 8, 16 CO2, and 2 times 9, 18 water. Okay? That is also a balanced equation. It is now balanced with the simplest whole number coefficient. And that's typically what we do for a balanced equation. We balance with the simplest whole number coefficients. All right? You will see equations balanced with fractional coefficients when we're talking about formation reactions sometimes. So we'll talk about that later. But in general, when you are asked to balance an equation, balance it with the simplest whole number coefficients. Okay, so that's balancing. Now let's talk about the meaning. Now I did want to highlight what I talked about above, this statement right here. A chemical reaction involves only the separation, combination, or rearrangement of atoms. Okay, so we are certainly rearranging the atoms. Let me scroll back up just a little bit. In this reaction, carbon was bonded to hydrogen in octane. Now carbon is bonded to oxygen in CO2. Okay, we are making and breaking bonds. That's a chemical reaction. All right, oxygen bonds were broken in an oxygen molecule, and we form new bonds to carbon, new bonds to hydrogen. Okay, it's just the rearrangement of atoms. All right, to form new compounds. All right, but it does not result in creation of anything new in terms of new atoms. We're going to get new compounds, but we're going to have the same atoms on each side of the equation, or the atoms are not destroyed. And there's a kind of corollary to this, conservation of mass. Conservation of mass. All right, mass is conserved in a chemical reaction. The mass on the left-hand side of the equation, what we call the reactants, is the same as the mass of the products. Okay, so that's a chemical reaction. Nuclear reactions, atoms are turned into different atoms. That comes way at the end of Chem 152. So you're going to have to wait for that. Almost this whole year, we're going to focus on chemical reactions. All right. So let's then talk about the second thing on my list at the start, was what do the coefficients mean? And let's take a really simple reaction that you're familiar with. Hydrogen gas, oxygen gas, going. Oh, and I balanced it for you. We should have balanced this, but double check that this is balanced. 4 hydrogens on each side, 2 oxygens on each side. Balanced equation. So we have these coefficients, and I'm going to write a 1 in front of O2. We do not write coefficients of 1. Okay, it's understood if there's no coefficient there that it's 1, but let's write it there. So what do those coefficients mean? Well, we could read them as a molecule ratio. 2 molecules of hydrogen reacting. I think you know this, but reactants are on the left-hand side of the arrow. Products are on the right-hand side. Okay, 2 molecules of hydrogen reacting with 1 molecule of O2 to produce 2 molecules of water. All right, there's your coefficients. All right, that's fine. That's true. 2 molecules of hydrogen react with every 1 molecule of oxygen to produce 2 molecules of water. However, and this is a big however, we will rarely read the coefficients like that. And I hope you see where this is going, because I've been talking about moles a lot in this course. We are almost always going to read these in terms of a mole ratio. Now make sure you note I say mole ratio. All right? Because it doesn't have to be exactly 2 moles of hydrogen reacting with 1 mole of oxygen to produce 2 moles of water, but they are going to react in that ratio in terms of moles. So 2 moles of hydrogen reacting with 1 mole of oxygen producing 2 moles of water. All right? This is how we will almost always read those coefficients, a mole ratio. Make sure you make a big note of that. It's all about mole ratio. And that leads us into stoichiometry. Because stoichiometry, all it is knowing how to go from moles of one thing in the equation to moles of something else. That's all it is. Stoichiometry, if we narrow it down to its very simplest form, moles to moles. Now we're going to expand on that. We might have grams come into play. We might have some other things come into play, but the basics are moles to moles. How do we do that? So let's very briefly talk about one of my favorite words, stoichiometry. Okay, so stoichiometry. Say we had a certain amount of hydrogen, and I wanted to know how much oxygen I needed to react with that. Okay, mole ratio. So let's actually choose an easy number to start. Let's say I have 12 moles of hydrogen. Okay. All right, so there's our question. This is stoichiometry. We start with 12 moles of hydrogen. How many moles of oxygen are needed to react completely with the hydrogen? Well, our coefficients are pretty easy. Our mole ratio is for every 2 moles of hydrogen, we only need 1 mole of oxygen. We only need half as much. Make sure you see that. Here's our coefficients. I'm going to use red. They tell you not to use red, but I like red. 2 moles to 1 mole. That's how we're going to read these coefficients. For every 2 moles of hydrogen, we need only half as many moles of oxygen. So if I react 12 moles of hydrogen, how many moles of oxygen do I need? 6 moles. Half as much. 2 to 1 ratio. 2 to 1 ratio of hydrogen to oxygen. Now, I chose a reaction with pretty darn simple numbers. But what if your numbers aren't that simple? How would we do this? Well, guess what we do? We do a unit conversion. We do unit analysis, dimensional analysis, whatever the heck you want to call it. So here's how we would do it. 12 moles of hydrogen. We want to get to moles of oxygen. What's the link from moles of one thing in a reaction to moles of something else? Here's a new conversion factor for you. So when I say this to you, how do you go from moles of one thing in an equation to moles of something else? You're going to say mole ratio. And if you want to be really weird, you can say stoichiometric factor. Okay, let's not go there. But it's also called the stoichiometric factor. But moles of one thing in an equation to moles of something else, mole ratio. And where do you get the mole ratio? From the balanced equation. We want to get to moles of O2. We want moles of hydrogen to cancel. What numbers do we plug in? Look up at the balanced equation up at the top here. You just plug in the numbers from the balanced equation. 1 to 2, 1 mole of oxygen for every 2 moles of hydrogen, and we get 6 moles of oxygen. That's it. That's stoichiometry. Piece of cake. All right? It can get harder because you might start with grams and have to go to moles first. Do you know how to do that? Sure you do. Grams to moles, molar mass. Okay? Once we get moles of something else in the equation, you might have to go from moles to grams again. Or maybe moles to atoms. Who knows? But you know how to do that too. All right? This is the key. Mole ratio is stoichiometry. Keep that in mind. It's probably the simplest conversion factor we've used yet this semester. The coefficients from the balanced equation. So let's just do one more question in this pre-lecture. Let's say we have this same 12 moles of hydrogen. How many moles of water are produced? Okay, so water is on the product side of the equation, so we're going to say produced. How many moles of water are produced, assuming, and we're going to always assume this, unless you're told otherwise, we're going to assume the reaction goes to completion. All reactants go to product, assuming complete reaction. All right. So we're going to start, same thing, start with 12 moles of hydrogen. How many moles of water are we going to get? What do you need to go from moles of one thing to moles of something else? Mole ratio. Okay? New conversion factor. I'm going to scroll back up just so you can see the equation again. What is our mole ratio between hydrogen and water? Oh, I erased by scribbling. It is 2 to 2 or 1 to 1. Wow, that's easy, right? That was easy. So it's 2 to 2, 1 to 1. So if I react 12 moles of hydrogen, let me write it again. There's our 12 moles of hydrogen. How many moles of water are we going to get? 2 to 2 or 1 to 1? 12 moles of water. That's all there is to it. So it's always that ratio based on the coefficients. Again, we really wouldn't have to write this out, but if you want to get practice writing the mole ratio, we're starting with 12 moles of hydrogen. We want to get 2 moles of water. So we put moles of water in the numerator. Again, unit analysis, dimensional analysis. We want moles of hydrogen to cancel. And then we just write in the mole ratio. You could write 2 and 2 if you wanted, because that's the actual coefficients in the balanced equation. Or 2 to 2 is the same as 1 to 1. Whichever way you want to do it. Moles of hydrogen cancel. And again, very simple calculation, 12 moles of water. All right. So that's all I want to say about stoichiometry right now. We will do more problems in class. But stoichiometry, this is the fundamental part of it. Understanding if you have moles of one thing in that equation, you can get the moles of anything else using the mole ratio from the balanced equation. That's all there is to it. That's it. The other pieces you already know. If I give you grams to start with, your first thought is, I need to get to moles, molar mass. Now I can do stoichiometry. If I then ask you to get moles of, say, water here, or not moles of water, what if I asked you to go to, I didn't want moles of water, I want grams of water. Can you do that? Yeah, absolutely. We know how to go from moles to grams. What do we need? Molar mass. Okay? Not so bad. What if I asked you for molecules of water instead? Could you do that? Could you go to molecules of water? Yeah, absolutely, right? How many particles are in a mole? Avogadro's number. Okay, so you see how we're piecing this together? So in the last chapter, we were like, okay, we need to know how to use molar mass as a conversion factor. We need to know how to do Avogadro's number. Now we're adding mole ratio or stoichiometric factor. Okay, so that's the new step. That's stoichiometry. Piece of cake. Well, not a piece of cake. We'll practice. We'll make sure you get this down. All right, I will see you in class. Take care.